I'll begin. Dear Heavenly Father, we thank you for this day. I thank you for these students and for the nice weather this morning. Just pray that you be with us, help us to glorify you in what we do, help us to learn what we need to about logarithms, and just pray that the students would be encouraged as they work just to do their best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So, here we go. Let's talk about logarithms and exponentials. So logs and exponentials. I suppose the first order of business is just to give you the definition, right? So if a is greater than 0 and a is not equal to 1, then f of x equals to a to the x. All right? This is an exponential function with base a. All right? Now, the graphs of those, let me just throw up the graph here right quick. The graph of that either looks like I'll draw them side by side. Although, of course, you could put them on the same graph if you wanted to. But the one shape is like this. This would be something like y, well, this is y equals a to the x with a greater than 1. The other possibility is the other way. This would be y equals a to the x with 0 less than a less than 1. All right. Either of these are called exponential functions. So the y-intercept is at 1, all right? The y-intercept is at 1 there. So just, token example, y equals 1/2 to the x could look like the thing above here, whereas this would be something like, oh man, I'm the dummy, 2 to the x. 2 to the x would be like here, whereas this one would be something like y equals 1/2 to the x. Now, what is 1/2? 1/2 is 2 to the minus 1, right? And 2 to the minus 1 to the x by the laws of exponents, which I'll soon write down, well, that's 2 to the minus x. See, so this makes total sense, right? If you take this graph, right, and you reflect it across the y-axis like that, you get that one. That's because it's just the replacement of x by minus x for appropriate choice of a, right? So there's a duality between base a and base 1 over a, if you're looking for it. All right? In both cases, right, as long as why can't we have a equals to 1? What's the deal with a equals to 1? It's just, if you have a equals 1, it's f of x equals 1 to the x, which is just the constant function 1, right? That definitely is not 1 to 1. But every other choice, right, if we have a positive not equal to 1, these pass the horizontal line test, they're 1 to 1, right? So what does that mean? That means we can define the inverse function, right? So, definition, f inverse of x is equal to log base a of x, right? And this is for what? Well, this is called log base a of x, right? As a function, this is the logarithm base a. All right, so we use this language log base a because it gets tiring to say logarithm. That's like a lot to say. Okay, and lovely. So if we, I should mention some important special cases. Okay, let's talk about some special cases before I get too much further. So special choices of base. Special bases. So one that I don't always lead with this, but a equals 10 is important. So if we have log base 10, we call that just log. Typically in American textbooks, this is called the common logarithm, log base 10, all right? Common log. There's also a equals to 2 sometimes is talked about, log base 2. I've seen notation LG for that. I don't have a name for this, but this comes up in like computer science, base 2 arithmetic, like log base 2, so LG. But what's far more often the case is the case A equals to E, which is about 2.71 dot 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 dot. All right, in that case, we call log base E the natural log. So more often than not, you'll find me using natural log in here to solve problems. If there's no preferred base on the basis of the problem, I'll almost always defer to natural log. If you look at your calculator, natural log has like natural log has got its own button. You don't have to go into a mode on this calculator, right? It's just there out on the surface of the buttons. It's usually a primary button. Natural log's a very important mathematical function. And so here's the deal. We have the following relations, always. We have log base A of A to the x is equal to x. We have A to the log base A of, let's say, y equals to y. This is for any x in the reals. All right, for any x in the real numbers. And this is for positive y, right? Or you could say for y, an element of 0 to infinity if you want to. If you prefer to speak in a way that's more confusing to college algebra students, there you go. Now, what do these two things here look like when we specialize them to the other bases? So like I'll just, these equations become the following. So like in base 10, we've got log of 10 to the x equals to x, and 10 to the log of y equals to y, all right? So that's how this notation looks like in the common logarithm. And in the natural logarithm, you've got this, natural log of e to the x equals to x, and you've got e to the natural log of x equals to, I was using y for this, wasn't I? And e to the natural log of y equals to y. And I'm just using y here for a second to try to emphasize the fact that what you input into the natural log, you have to be careful. You have to input a positive thing into a natural log, or into a logarithm more generally. Whereas the exponential, what's the domain of the exponential functions? Everything, right? So the domain of the exponential is the whole real line, right? And that's equal to the range of the logarithm. And the range of the exponential, which is positive numbers, 0 to infinity, that's equal to the domain of the logarithm, right? So there's always this complementary nature of the function and its inverse function, okay? Okay, so these are the basics, right? Let's work an example. A graphical example. So example 1, graph y equals to, let's say, 3 plus 2 to the minus x plus, I didn't do that. Let me say 2 to the x minus, 3. There. Oh, I don't want to do 3 and 3. Let me change this first number to something different, like minus 1. All right, minus 1. There we go. Okay, I'm happy with it now. All right. So I was trying to do something a little bit different than the last two sections of college algebra. If you watch the start of the videos, I did a graph like this, but with different numbers. So I wanted to, anybody who wants to see more examples, I wanted to arrange it like that. So how do we graph here? Like, what's the basic thing is, we start with our y equals 2 to the x graph, which is this, right? Take that graph, right? What's the y-intercept? It's got this point. It's got this point, 0, 1, right? Can you tell me another point on the graph? How about this? Up here, there's the point. What if I put in 1, what do I get? Plug 1 into x, you get y equals 2 to the 1, which is 2, right? So the point 1 comma 2 is also on this graph. Now, what do I want to do to that graph in order to get the desired, function there? We call it f of x. How's the graph of f of x related to? See this? This means they're washing the board with water. If they were washing it with board cleaner, it wouldn't smudge like that to start with. Anyway, so what? What do we do? What transformation do we want on this graph to get f of x? Okay, left, what? Ooh, nope. We want down 1. Remember, it's directly what it appears to be when we add or subtract from the formula, but when you're going the input to the formula, it's kind of opposite our intuition. So replacing x with x minus 3 moves 3 not to the left, but to the right. Right. Okay. So yeah.
Oh yeah.
Right. Yeah. So down 1, right 3. That's our graph. And so let me do it. I'll try. So I'm going to go, and so I would point out every exponential function has kind of a horizontal asymptote. I mean, it is a horizontal asymptote. It just doesn't go both ways, right? Like the horizontal asymptote for the base less than 1, it's to the right, right? If the base is larger than 1, the horizontal asymptote's to the left. But one way or the other, it's going to go to 0, either to the right or to the left. So anyway, this one, down 1. So we're going to have, this is kind of like my base for the graph. So this behaves like the x-axis does there. I go down 1. And so I go down 1 and right 3. So this would take 0, 1 to where? So down 1 would be 0, 0, right? And then right 3 would be 3, 0. So let's see here, something like that is my new point there. And this 1, 2 goes to 4, 1. So that's like here. But there you go, it's basically this. Right, there you go. That's y equals f of x. What's the domain and range for this one? And if you're not content with, you could track more than 2 points, right? You could track oh man, is that right? 4th? Did I do that right? I don't think that's 4, 3. Where should that point be? I go down 1, right? So I go from 1, 2 to what? 4, not 4, 3, but 4 what? 1, 2 goes down 1, right? So I go 1, 1, and then I go over 3. So I should be doing 4, 1, right? Not 4, 3. I'm a dummy. I was like, that doesn't look like 4, 3 on my graph. Well, yeah, because it shouldn't have been. Okay? There you go. There's the graph of y equals f of x. What's the domain and range for our function here? Uh-huh. What's the range? -1 to infinity. Now what do you guys think? Is minus 1 included or excluded there? excluded, right? Because it approaches minus 1, but it never gets there, right? So
Is it, um, like, wouldn't it just be like infinity?
with the range,
Yeah.
it never gets past this green line, though. Like it's always above the green line. So just like the regular one back here, the range of both of these was 0 to infinity because it never actually gets below the x-axis.
Yeah.
So the x-axis is like my green dotted line over here.
Okay.
Yeah. Okay, so next up, let's talk about the properties of exponentials and logarithms, yeah? Some of the properties you should be familiar with. We might have even talked about them in, the first week of classes. I don't remember. I don't think we focused too much on these, but in a different semester I might focus more on these at the start. Although it doesn't generally lead to feelings of contentment and harmonious feelings for the students, because I find that, generally speaking, students are really kind of shaky on these. And it's not just you guys. When I teach calculus, at the start of calculus, I find 70% of the students really don't have properties of exponentials down pat. It's not hard for me to like trick them about these things. And so anyway, let's just talk about them. So here they are, a to the x. And when I write them, you're going to be like, well, I know that, right? A to the x plus y. That's 1. This is if we have like bases, we multiply, we add the exponents, right? So I think that it's more the application that you guys are shaky with. Everyone's probably going to agree with these as I write them. Like, oh, I've seen that before somewhere, you know. We also have, if we have a to the x to let's say p power, we get a to the xp, right? Like that, we multiply exponents in that sense. Also, there's some special cases, right? Like you guys know, a to the 0 is 1, right? A to the 1 is a to the minus 1, 1 over a, right? We're all good on these, yeah? So these are the laws of exponents that we need to work problems on occasion, yeah? We'll see that. There are also logs. So what are the properties of logs? Well, correspondingly, and perhaps surprisingly, we have that log base a of, let's say, trying to decide here. Actually, let's save ourselves some writing. What I'm going to do here is I'm just going to write just a generic like log, and understand that this log you could replace with log base a, you could replace with natural log, you could replace with LG. These things are true for any base, okay? But if I have like log of a times b, I get log a plus log b. All right. If I have the log of a over b, I get log a minus log b. If I have the log of a to the power p, I get p times log of a. All right. So these are properties of the logarithm. And there's one other thing I can write generically here, which is that log of 1 is 0. Okay, the log of 1 is 0. Why is the log of 1 0? The log of 1 is 0 because any power, any a to the 0 power is 1, right? So like the reason that this is true, this is interchangeable with the statement that a to the 0 is equal to 1. anyway, let me write a few other things here in the more sort of specific language. So like log base a of a is 1. Log base a of 1 over a is minus 1. And a few other things here while we're at it. Natural log of e is 1. All right. Log of 10 is 1. And here I mean log base 10. Okay. But okay, anyway, so yeah, these are the properties of logarithms, property of exponentials. And if you wanted me to, we could prove the properties of logarithms can be derived from properties of exponentials, right? And if we have time, I'll probably do that next week if I do it. I'm not going to do it today. We're going to focus on solving problems today. Okay, but you can derive these identities here from these. You just have to kind of look at it the right way. It's a little bit sneaky because the way that the log and the exponential are related is a little bit sneaky, right? Remember what we wrote for the inverse function? Remember definition of inverse function? One way we could have defined it was if y equals f of x, then f inverse of y is equal to x. This was the definition, one of the things I wrote for the definition of inverse function. So what that translates to in our current context is that if y equals a to the x, then log base a of y is equal to x. And so that's just a little bit foreign to our intuition, right? Like the role of x and y get flip-flopped, and it just kind of boggles your mind a little bit if you're not watching out for it. Like, I mean, I can show you examples of it. Let's see here, like example 1, example 2, right? Example 2. If we have, for example, since, 100 equals 10 squared, right? Get log of 100 equals to 2. Or since, well, let's see, I'm trying to think of another one I can rattle off here. Well, I think that's sufficient, but I usually think of it like this. If I'm looking at like natural log of, for example, e to the 13th, I just go, oh, okay, so natural log and exponential are inverse functions, so that just simplifies to 13, all right? And that's just kind of it. Sometimes what I'm saying is I don't always have to go back to that, what I've written in blue at the top of that board there, you know? Sometimes we just, I would say the basic thing to be aware of and to look for is that the exponential and the log are inverse functions. They cancel each other, okay? Okay, so let's work a few problems then that are more interesting than those. Erase some of my work for here. And work here. Probably don't need these anymore. So I also have forgot to explain to you, and I really should, why is this base e of interest to us, right? I didn't explain that. I just kind of just pulled this number out of my hat and said, well, it's called e, right? But why is e? Like, what's that about anyway, you know? And so the e is in honor of, probably one of the most important mathematicians that's ever lived in the Western tradition for sure, named Euler. Euler lived in the 18th century, and very interesting guy. Born-again Christian, lived to a ripe old age, was blind the last probably decade or so of his life. I forget exactly the number, but he was blind for a while, and he still wrote tons of math papers. because he had like a scribe and, you know, kind of like Peter. And I'm not saying Peter was blind, but I think it's agreed that Peter didn't write down like what he wrote. Anyway, so here's the deal. To understand the exponential, you can understand it this way. If we look at y equals 2 to the x, all right, it goes from like, let's see here, 1, something like this, all right? So here's the graph of 2 to the x. You got that? What does the graph of 3 to the x look like? The graph of 3 to the x, it's a little bit lower, right? It goes through a third rather than a half over here, and instead of going through 2, it goes through 3. So it's below the half over here. It crosses through the y-intercept just the same. Y-intercept is 1 for all these dudes, and it goes up like that, all right? And if we, so I used Desmos to look at this in a couple of sections, and it, I don't know, it like wasted 10 minutes of class, and it really didn't accomplish anything. I think it's better just to draw it on the board. So if you look at this, right, you can talk about what's called a tangent line. What's a tangent line to a function? If you can imagine drawing a line that just kisses the function right at a point, and it's the best approximation to the function by a line close to the point, right? So you just kind of imagine like, so some of you have studied high school geometry. You know what a tangent is there, right? It's the line which is just kissing the circle at one point and it's perpendicular to the radius. So the idea for a tangent to a function is similar. So the tangent to the purple line is kind of like that, right? If you see it, it's kind of like that. At the tangent line at the y-intercept, it's kind of like this for the purple line. If you look at the tangent line to the red line, it's something kind of more like this, all right? And if I did that carefully, what you'd see is that the tangent line tangent to y equals 3 to the x at the y-intercept, 0, 1, has slope greater than 1, all right? And you could also see that the tangent to y equals 2 to the x at 0, 1 has slope less than 1. Okay, so the y equals 3 to the x has bigger than 1 slope, tangent line at x equal to 0, whereas y equals 2 to the x has slope less than 1 at the y-intercept, right? And it's not hard to see that you can choose other values other than 2 and 3, right? You can look at the y equals 2.1x, right? Like the y equals to the 2.1x is going to be between these two guys, right? Y equals 2.2 is going to be between these guys. 2.3 to the x is going to be between these guys, right? And it turns out, if you study this, that there's a very specific choice of base between these two. I should have made this bigger. This is really hard. Up to the wiggling of my drawing, like this, okay. That, oh man, look at all this. I'm the worst cameraman. Sorry, people not here. They didn't miss much though, did they? I just drew that picture. So I will redo the thing. The tangent line to the 3 to the x is bigger than 1, like that. The tangent line to the 2 to the x is smaller than 1, like that. So between those, you can find the green line, which has slope 1, right? The exponential that has slope 1 at the y-intercept, this is called this is the e to the x function. Okay, so definition, the choice of a equals to e, which makes y equals e to the x have slope 1 at 0, 1 is e equal to 2.718 blah 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 blah, and this is the so-called base e, right? This is not, and so as a point of language, and this is what my brother says anyway, he's like f of x equals e to the x. It's not an exponential, this is the exponential, because it's a special one. And by and large, if mathematicians are talking about the exponential function, they're talking about this one, all right? It's the special choice of base, which has that property of having slope 1 at the y-intercept. And actually, it's more interesting that the slope, it turns out that the slope of the exponential function, this e to the x function, its value is equal to its slope everywhere. So if I go out on the green line over to like 1, and if I look at the point 1 comma e, what's the slope of the tangent line there? It's e. If I go to 2, where the value of the exponential function is e squared, the slope of the tangent line there is e squared. And this goes on and on. So it's the function, it's a weird function. It's a function whose value matches its slope everywhere. And that makes it very special. And it appears in all kinds of science and engineering and such, of course. All right. Okay, enough about that. I do owe you a blurb about what E is. So now we've blurbed. So let's go on. Do problems like your homework, right? Example 4. So I learned from my mistakes. I got fished in, like in your homework. In your homework, one of the earlier problems is much harder than some of the later problems. Maybe you should skip it as a warm-up. So what I'm talking about, and we'll work this problem, all right? But it's kind of a doozy. Well, I mean, it's not impossible or anything. It's just kind of ugly. Ugly. Number 19. I would do like, I don't know, number 20 and some other ones. I would save 19. If you skip over 19 and come back to it, it wouldn't be a bad idea. 19's kind of tough. Let me work out something easier here. So I'll do like number 20 to start with. So number 20 is something like this. 2 to the 2x minus 3 equals to 16. All right. Now, here's the deal. When we're solving an equation like this, we can use logarithms to help us, but we don't have to. All right. There are ways of doing these problems without using logarithms, and so let me start with that. Yeah. What is 16 as it relates to 2? Can you guys put 16 in terms of something in terms of 2? What is 16 as it relates to 2? 2 to the 4th. Aha. Very good. Is that an obvious step? No, right? That's a kind of clever step. You have to have a number sense, a memory that, oh, I've seen this number 16 before. It's 2 times 2 times 2 times 2, right? It's 2 to the 4th. Just counting. Whenever I verbalize something like that, I'm always like, did I say too many 2's? But there it is. Now, here's the deal. Fun fact. If we have a to the x1 equals to a to the x2, that implies x1 equals to x2, right? This right here is the 1-to-1 property of a to the x, right? And this is not a surprising fact for us. This is what we were talking about last time, right? 1-to-1 functions are the ones that are invertible. This is the 1-to-1 property. If the values are equal, the inputs are equal, right? So if you understand that, right, then once you have, 2 to the 2x minus 3 equals to 2 to the 4th, well, that implies 2x minus 3 is equal to 4. And then we can solve for x, right? So we get 2x equals to 7, x equals to 7/2. All right, so yeah. There are problems like this that we can work. Let me work another one here. Man. what if we were up against example 5, e to the 3x plus 2 squared equal to e to the minus x. How would you solve this? If at any point I try to erase this board, this part of the board today, you should yell at me, stop! All right, because I want to leave this here because we're using these, all right? We want to use basically this one here. See, because we've got an exponential to a power, right? So when we have that, we multiply the power into the argument. So this gives me e to the 2 times 3x plus 2, if you like. Or you could put the 2 over here. I mean, you can, look, this is equal to a to the px, right? Multiplication commutes, you can do it either way, right? And we get that's equal to e to the minus x, yeah? So what do we have? We've got 2 times 3x plus 2 equals to minus x by the one-to-one property of the exponential, right? Oh, by the way, I should mention, common notation is x equals e to the x. Like sometimes I'll use this, especially in calculus, if I want to make the thing that's going into the exponential really big so you can see it nice. I'll use the notation exp of whatever rather than just e to the whatever. This should not be confused. Some of your calculators have like EE. There's like EE notation. EE notation is something like powers of 10, but don't ask me about that because I don't use it. I'm just saying if you see this, beware that this is, like if you have EE1 or something like that, that's something like 10 to the 1 or something like that. That's something else. So that's not going to appear in here except that I wrote it on the board, but let me make it go away. Haha. All right. So then you can solve for x, right? Can you? Can you solve that for x? So we've got what, 6x plus 4 equals to minus x, which gives me 7x equals to minus 4, which then gives me x equals to minus 4/7. All right. Let me show you another one here. See where my camera's pointing. What if we're going to solve example 6? Let's go to solve 256 to the, let's say, 5x equals 64 to the x minus 3. Can we solve this? So the last two examples have been relatively obvious that we should have worked with. Like the first one was base 2. This one was just base e. It's kind of in your face. It's a base e problem, right? How about this one? What do you do here? I think those are both powers of 2, right? So we can rewrite these as 2 to the whatever, you know? So like 2 to the well, I think we just said 2 to the 4th is 16, right? 2 to the 8th is 16 times 16, but let me go smaller here. 2 to the 6th would be 64. 2 to the 7th would be 128. 2 to the 8th would be, 256. Oh, there we go. So this is 2 to the 8th raised to the 5x power, right? And 64 is 2 to the 6th raised to the x minus 3 power. So I can rewrite this as a 2 to the something problem, right? And so I have 2 to the 40x equals 2 to the 6x minus 18. Then by the one-to-one property of the exponential, this gives me 40x equals to 6x minus 18, right? Which then we can solve. So we've got 34x equals to minus 18, which gives me x equals to minus 18 over 34. Which is by no means obvious, right? If you go back to the original equation and you think, oh, of course, if I put x equal to minus 18 over 34, then 256 to the minus 5 times 18 over 34 power will be equal to 64 to the minus 18 over 34 minus 3 power. Obviously, right? No, no one would guess this, right? My 10-year-old self could never guess this. You know? Part of the reason I didn't like algebra to start with is I was always given problems that I felt like I could just solve in my head anyway. Why bother with the symbolics when I can just figure out the answer to the word problems, right? We should we should do things like this to children to like humble them to realize, oh, you need symbolics to solve certain problems, right? You can't just do everything in your head. Okay, anyway, so that's that. Now, I still think there's something fundamentally, I have a fundamental sense of ill at ease with all of these problems because they're all relying on this like initial step of, oh, those are both 2 to a power, or the other one, oh, that's really 16 is 2 to the power, right? Or here's another one. Example 7. I'll stick it here. This one's kind of short. 1 over 16 equals b to the minus 4, right? How do you solve that? Well, you go, okay, well, that's 2 to the minus 4. Well, excuse me, that's 1 over 2 to the 4th, right? Which really gives me 2 to the minus 4 equals b to the minus 4. So what's the solution? Two equals b, right? Now that that's not the one-to-one property of the exponential, right? That's really just us getting lucky there. In some sense, because how do you know that that's the only way you could solve that, right? I mean, obviously putting b equals to 2 solves that equation. It's just manifest, it's in our face, you know? But could you derive that through some sort of more systematic means? You know, is there a safer way to operate here? There is, I'll show you in a minute. One more of these though. So this is like number 25 in your homework, example 8. So here we've got the square root of 2 raised to the x plus 8 power equals to, and what I've done today, some of these examples, is I've changed the problems in your homework just a little bit, which has made the answers ugly. The answers in your homework tend to be nicer. They're like 3 or minus 3 or something like that. Stupid, but so this one probably is going to have a nice answer, relatively speaking. Yeah, kind of. What do you do here? So what is 2, square root of 2 is what? That's 2 to the 1/2, all right? To the x plus 8. And this is 2 squared to the x, yeah? So we can, it's all 2's, right? And so this is 2 to the x plus 8 over 2 equals to 2 to the 2x. Then by the one-to-one property of the exponential function, we get x plus 8 over 2 equals to 2x, which then you can solve, right? This gives us what? Well, you solved that, yeah? What'd you guys get? So I'd multiply by 2, you know. That gives me x plus 8 equals to 4x, which then gives me 8 is equal to 3x, which then gives me x is equal to 8 over 3. All right. So these problems are relatively easy in the sense that if you can see both sides as being the same base, and then you can use the one-to-one property exponential and you can solve them, right? There's not a logarithm to be seen here, right? Did I use logarithms to solve these? Not really. I just used the one-to-one property. And so that can be a very nice method of solution. But I do think that knowing about the logarithm once you know about logarithm, you can solve all the problems we just solved without being clever. You can solve all the problems I just solved just by taking the log of both sides and applying properties of logarithms. You don't have to be clever. You can use brute force. Let me show you how this works in a specific example. This is like number 23 in your homework. I'm faced with r to the 2/7 power equals to 4. All right? So if you want to solve this, one way you can solve this is just to take the natural log of both sides. Well, I guess natural log is kind of too lazy. I could take the log base 4 of both sides, okay? So if I take log base 4, this board, look at this. Sorry, it amuses me. R to the 2/7, like I need to bring my, I mean, it would be unfortunate if some vandal came in here on the weekend and like screwed this board to the wall properly without, you know, putting in a work order and things like that. If they just came in here and put a screw in, that would be unfortunate. It's kind of like where my brother works. There was this one time this guy came in, he came into his office after the weekend, and like his carpet, which you know gave him trouble with his allergies, had been removed, and like hypoallergenic wood had been installed on the floor by somebody in the weekend. Those vandals. So that kind of thing happens sometimes. But okay, so you guys have not dealt with bureaucracy enough to understand these jokes, but it's okay. Like, you know, the Lego. You guys have seen the Lego movie, right? It's not really a children's movie. You have to work in an office for at least 10 years to properly appreciate that movie. Like you can't really appreciate the forced groupthink and the requirement to, I don't know, anyway. But okay, so if I take log base 4 of both sides, I did that. The reason I did that is because log base 4 of 4 is easy. It's 1. Okay? And then this is going to give me what? This is 2/7 log base 4 of r equals to 1. I'm starting to regret this. Oh well. So this gives us log base 4 of r equals to 7/2. Yeah? And then how do I solve for r? How do I get back to r? What's the natural enemy of log base 4? It is the 4 to the something. So then I exponentiate both sides. I do 4 to the log base 4 of r equals 4 to the 7/2. But this, by inverse function construction, is exactly r again, r. And that's 4 to the 7/2. Now, what is 4 to the 7/2? By the way, that is 4 to the 1/2 to the 7. What is 4 to the 1/2? Yes? Why did I flip the what? Oh, I solved for the log. So I wanted to isolate the log. So I multiply both sides by 7/2. 7/2 times 2/7 gives me 1. So I'm just divide this to the other side, you get 7/2. You know, 1 over 2/7 is 7/2. So what is 4 to the 1/2? 4 to the 1/2, that's just a weird way of writing the square root of 4, which we all know is 2, right? Hey, so this is really just 2 to the 7th, which I happen to know is 128. So the answer here is 128. Whew, I thought I was going to have to get out my calculator for a second there, but I guess I didn't. Now, actually, this is really dumb. What I just did is incredibly dumb. Well, maybe that's the wrong word, but it is. Look, so here's the thing. You know, you live here, right? There's a store here, right? See the store? It's across the street. Your wife tells you go get some milk, and then 3 hours later you came back, right? Because you did this. Like that, right? That's kind of what this is. There's a much easier way. I didn't need logarithms. I wanted to introduce logarithms, so I made it about logarithms, but I didn't need to do that. There's a much simpler way. How do you fix this? How do you solve for r? You just exponentiate both sides to the reciprocal power. So we do r to the 2/7 raised to the 7/2 power, both sides. And when you do that, you get r to the 1 equals 4 to the 7/2, which we just worked out as 128. That's this root. You know? All right, let me try to find a problem where we actually need logarithms, because that's not the one. All right, let's see here. Well, some things just we'll find it. I will show you an equation where I need logarithms, and then we'll get back to the other problems in the homework. Example 10. See, if I'm up against something like this, 2 to the 2x plus 1 equals 3 to the minus x plus 7. Something like this, I have no choice. There is no hope for this problem except to use logarithms. Because there's pretty much, unless you're like just really, really creative, you probably can't rewrite 2 as a power of 3. Can you write 2 as a power of 3? All right. Okay, so what I'm going to do here is I'm going to take the natural log of both sides, because, you know, and then by the power property, we get 2x plus 1 times the natural log of 2 equals minus x plus 7 times the natural log of 3. And now I can solve for x, right? So let's see here. Put all your x's on one side. So I've got like 2x log 2 plus x log 3 equals to minus log 2 plus 7 log 3. Factor the x out. We've got x times 2 log 2 plus log 3 equals to minus log 2 plus 7 log 3. And now divide, we solve for x, yeah? X equal to minus log 2 plus 7 log 3 divided by 2 log 2 plus the natural log of 3. And that right there is a perfectly good answer. Of course, we might want to do better. We might want to like give our answer as a decimal. we might want to like use properties of logarithms to simplify the numerator and the denominator. Let me show you how that goes. So this, we could simplify our answer a little bit, right? One thing I could do would be something like this. This is really the natural log of 3 to the 7th divided by 2 over the natural log of 2 to the 2 times 3. So I could write it as that. I mean, I'm not sure that's really so much of an improvement, but my point is that's a simplification you could make, okay? So we need to talk more about those kind of simplifications with natural logs, because you really need to think about how to make these kind of modifications to truly internalize these laws, all right? So we need to work more problems like that in here next. Okay? But my larger point, do you see how we needed the logarithm here? Like the approach we've been taking up till now didn't work. The one-to-one property doesn't help us here, right? Uh-oh. I think I'm about to erase something I never... Oh, you're fine, you're fine. All right, so keep working myself into the corner here. All right, let's erase the evidence. Let's see here. So, example 11. Let's just work something. So here's one. We're given 5 to the 4th equals 625. All right, and you're asked to write this in logarithmic form. What's that mean? So basically just translate this into logarithms. This says that log base 5 of 625 equals to what? So can you guys tell me what to do up there? What is the answer there? It's 4, right? That's it. This other problem here is the sort of the other way. So here I'm given a logarithmic equation. I'm told to write it in exponential form. This corresponds to saying what? This is corresponding to exponentially 5 to the 2 equals to 25. Okay, that's the corresponding exponential equation. Let's see here, example 13. Suppose you're going to solve log base x, ooh, weird, of 64 over 343 equals to 3. How would you do that? So we'll chew on that for a second here. Example 14, we'll look at log base 49 of the 9th root of 7 equals to x.